Hello. Please give me a thumbs up. Click through. Slice. Load. Hell yeah. Okay. We got Crux coming up.
Hey, Const.
Hey, so it's very good that we have Stefan up on stage today because I'm a mathematician, I'm a computer scientist. I can hold my own at a cocktail party talking about quantum mechanics, but I- it's a very complex thing. As I understand it, even people that study it their entire lives are kind of confused. But Stefan, you, sir, are actually a physicist, and I'm assuming that you'll be able to take all the hard questions.
I mean, it's a deep rabbit hole, man. I'm a little bit rusty with my quantum computing lingo, but I think I can at least engage in a reasonable conversation that the audience can enjoy. I think the peak of my quantum computing career is I built a simulator of a photonic quantum computer at an IBM hackathon about 5 years ago. But I have some understanding of this stuff, and it's a really, really cool space.
So before our guest gets up here, why don't you give us just a deep dive? Tell us about the history of quantum mechanics, what it is, Heisenberg's uncertainty principle, all the things that people will need to know just to get up to speed before we get into quantum computing.
Wow, you could have briefed me on that before you pulled me on stage, mate. Um, a brief introduction to quantum mechanics. Well, I think that it gets interesting when you think about the limitations of classical computing, which is everything is represented as a very exact piece of data in a transistor, so zeros and ones effectively. And of course, this is a very, very effective way of performing computation, but there are certain problems that require massive, massive phase space exploration or massive, massive memory requirements. And quantum computers are really, really good at sort of residing in a limbo of juggling lots of potential candidate answers and then sampling from basically things that are not just ones and zeros, but something that can sort of be balanced between the two of those. It's like a stochastic computer because nature is stochastic. Quantum mechanics is inherently about sampling from probability distributions, and quantum mechanics are a way of tapping into that extreme efficiency in certain problem domains. But I think a real expert has now stood on stage, so I'm going to quietly recede from from my lecture, and I'm going to let him continue the introduction to quantum mechanics and quantum computing. Beyond NISC, hey,
Hey man, how's it going? I thought you
hey,
were on a
good.
roll.
Yeah,
Is-
I often sound like I am, but it's rarely true.
So I'm a bit nervous that Const is going to ask me to explain a crazy quantum mechanic principle on the fly, man. That was a crazy drop on Crux. Also, by the way, guys, we should have Bongo Cat Feynman joining us also. So if he raises his
He's
hand.
Yeah, he's coming up now.
All
Yep.
right.
Hello, everyone. How's it going?
Welcome, Mr. Bongo Cat Feynman.
Thanks.
Yeah. So well, I'll be really interested as we're going here how long it takes before somebody calls out my name in chat. You're more than welcome to say it if you know it. I will dox and slide number 2. Oh man, JB Ring, you got it already. Holy smokes. Record time. Well done, guys. Yeah.
I see Richard Feynman on there.
Yeah, right.
Oh man, I wish. Anyway, thanks for having us, guys.
Very cool.
So I'd be happy to just keep it like informal and chat for a little bit. I'd also be super happy to jump into kind of prepared material. I was actually going to jump into not the technicalities of what quantum computers are, but I was actually going to start off going pretty deep into kind of why quantum computing is really pretty critical right now and why there's a market for it. And I'd be totally happy to dive into that, or I'd be happy to spend just a little bit of time hanging out before we start.
Well, I don't want to ask you any questions that you guys are going to go and ahead and answer anyways in your slides. So why don't me and Crux will leave our questions. Hopefully they'll be slightly more informed by the end. Um, and we won't sound so doofus like. And we'll just go straight in. So like I'm sure in your slides you're going to present yourself and stuff like that. If not, we'll definitely ask you at the end.
Yeah. Okay. Sounds awesome. Let's just jump in and do it then. Yeah. So we will keep this pretty casual. We do have like prepared material. Like I could tell stories all day long, every day. But do feel free to just kind of steer wherever you want to go as we're going, and we'll take you and your audience to that destination. So again, my name is Bob. I'm here representing Qubit Tensor Labs, and we're really excited to be here today. We're going to take you through kind of a journey where we talk about why quantum first and kind of why quantum now. I also want to talk about why bit tensor, which may feel obvious to all of you guys, but to be honest, it was a little bit of a surprise for me, and it was like an exciting surprise on the upside. So we'll talk about that. We'll talk about the progress that we've made so far, and we'll talk about the vision of sort of where we're headed next. And then I'll be really excited to share some of the kind of big evolutionary thinking that we've learned from what we've already done in the last section as we go. And like I say, I can be a storyteller and just talk for a long time. So I'm going to force a break between each of these sections, but like really do feel free to just jump in and drop your questions on me. So yeah, about me, I'm Bob Wold. Nice job calling it out, guys. I've been blown away with how good you guys are at information discovery. A little bit about me. I've spent 25 years in industry. I'm the founder of a traditional quantum startup called Quantum Rings, which is, very much like a, I don't like I almost want to say like, real world traditional startup, although like the real world is way less exciting than, the world that we all live in here, to be honest. I've always been a deep tech enthusiast. I've also been like a massive skeptic, and I was a huge skeptic of crypto in general, which sort of, I will say, started me off kind of assuming that this journey was going to be sort of a quick little dip your toe into, the exciting world of crypto. But man, I decided I want to dive in head first. This is great. We're based in Boulder, Colorado, and some people have asked about the logo. That's totally the Boulder Flatirons. So if you guys like Google Boulder Flatirons, it's like a distinctive mountain range right by Boulder. And I go by Beyond Nisk. All right, so enough about me. Oh yeah, the one thing about me, yeah, I've got, I am bullish on this market now. So why quantum? Well, quantum holds the promise to transform the world. That's like a super hypey thing. We'll have to dive into figuring out what that actually means. But Crux was actually onto it at the beginning, which is basically that like traditional computers are limited by how much information you can encode into them, like how far you can search within a search space. Quantum computers have this crazy thing where you can like encode the constraints physically into a computer, and it can represent all possible states in a space simultaneously. And so what that basically does is it can be applied to a specific set of problems that are like super big problems, super valuable problems that hold the promise to transform the world. And so like when I tell people about this in my day job, I focus on the fact that my grandchildren hopefully will live in a world where we've discovered cures to the most harsh illnesses. We can potentially cure AIDS, potentially cure cancer, because real-time computational simulation of new drugs will be enabled. Where, you don't think necessarily about how far you can get on your EV charge, because we've discovered better batteries that can charge faster, hold more energy, that have a lower impact on the earth to mine them. Where, we're no longer faced with like just the goods that are produced not being with the people that need them, because we can optimize supply chains, where today we have to approximate those optimizations because of computational limitations, or worlds where everybody's 401k looks a lot bigger because portfolios are being optimized. And it's not just sort of a directional promise. McKinsey did a study where they actually looked at each of these problems and experts in each of these fields and mapped the specific problems with the market that they were going to create and with the functionality of quantum computing and quantum algorithms. And they estimated that the first market's a $400 billion market. In the materials space, you have a $500 billion market, 600 billion in logistics, and 600 billion in finance. Now, I sort of misquoted that. It's not a market. That's the economic value creation by solving these problems, meaning that, we're unlocking by 2035 potentially $2 trillion in economic value if quantum computers can hold their trajectory, which is pretty damn exciting. And so, I'm hoping, Const, you're feeling good right now. Are you feeling bullish?
I am. But how does it all connect to BitTensor though? This is the big question.
Yeah. All right. Let's get there. But well, before we do though, I just gave you like the peachy story, so let me also tell you the real side of it too, and then let's connect in BitTensor. So, you're like, okay, well, if you can do all this awesome stuff, you're going to totally revolutionize the world. Then, why didn't you just cure cancer already? Right? Let's do it. Let's go. Well, it turns out that quantum computers are really, really hard because they require you to isolate physics and stop them from physicking with the rest of the world, right? And so that's why you see these things in these giant super refrigerators that get down to 0 Kelvin, right? Physics are very hard, and so in the real world, there are very few of these computers, so you got to wait in line. They're super noisy and error prone. To put some numbers on those. I have to wait hours or days for quantum computer. Like yesterday, I had to wait 12 hours to run on IBM's quantum computer, and that's not abnormal. It's not like that was a long wait time. They have huge error rates between 0.1% to 1% per operation. So that's not per program. That's essentially per line of code in the quantum world. And they cost, if you think GPUs are expensive at $2 to $4 an hour, try spending, $5,000 to $15,000 per hour on them. And so if you're the people saying oh man, I'm going to go solve these billion-dollar problems and transform the worlds, you are blocked, right? You're sort of stuck by this. So maybe you're not feeling quite as bullish anymore. No, it's still good. It's still good. So the people that know kind of know that there's two sides to this story. And so if you look at Jensen, CEO of NVIDIA, he'll talk about how exciting it is because they're going to solve these exponential problems like simulating atoms and molecules for drug discovery. You're just going to need several million physical qubits. Or you can look at Sundar from Google, and he'll say, yeah, we're going to totally learn the basic structure of molecules that we're sort of missing today, except you're going to need a totally fault-tolerant quantum computer to do it. Still a bull. Or Satya from Microsoft, who talks about, lossless power grids, carbon capture from atmosphere, quantum computers so powerful we can model nature itself. Totally a bull. And so all of these guys are equal parts excited and not excited about it. Or they're excited, but they're realists about it. But the cool thing is that, and this is sort of tying into why BitTensor, you guys probably are super familiar with AlexNet. I probably don't need to explain that to this audience, but just in case. In 2012, AlexNet was released, and it kind of blew people away with how accurate that model was. And then once they put that model out there and everybody else started working on this problem and really democratizing it, thousands of smart people trying to do better, you can see that in the 7 years that followed, you could get AlexNet performance with 44 times less compute. And that's freaking awesome because lots of smart people working on these problems get you to innovation. Well, history is kind of starting to repeat itself in that if you take a look at some of the really exciting quantum things, in this case, those RSA ones are on breaking encryption. FOMOCO is about, simulating a very important molecule. There are these different quantum algorithms. You can see that how big a quantum computer is going to have to be to solve these algorithms is getting better because the scientific community that's working on them is making the algos more efficient. You can also see that quantum computers are getting better, the qubits themselves are getting better. This particular chart happens to be from Google's, Google's Willow processor. This is about coherence times of qubits, which, one of the users on Twitter had asked us about coherence times. They're getting better. Error rates are getting better. Error correction's getting better. All the charts are in the right direction. And so when I think about that, I was reminded of this DARPA slide from the DARPA QBI conference that I was at in DC in February, where they put up this chart of all the different quantum problems scatter plotted across the size of quantum computers on the bottom and the number of quantum operations. And so you can sort of see that some problems are going to require huge numbers of qubits. Some are going to require just a few qubits. But the cool thing is that the quantum computers are getting better, and we have these problems getting easier. And so the conditions are sort of like just right for this thing to go to the moon. Okay, this isn't like a crypto, like to the moon. Well, maybe it's, make no financial projections, but I mean, like quantum is ready to go to the moon, right? The problem is going to be that scarcity is going to remain. And I literally was talking to the number 2 quantum computing company in terms of logical qubits, and I asked them, how much is it going to cost to buy one of these quantum computers? He says, I can sell them for $N million. And I'm like, that's awesome. How much is it going to cost when you have 100 logical qubits? And he said, I'm not going to sell them when I have 100 logical qubits, because once I have 100 logical qubits, I'm going to solve the world's, like these handful billion-dollar problems. The only people are getting access to them is we're co-developing IP. And so power and scarcity make people do strange things, right? And I think that's like what the quantum world is like, even when it's bad for everybody in the end. And so that is why BitTensor couldn't come at a better time. So when I first saw it, I was first impressed with your graphic, but I was quickly way more impressed with what came after that. So I was actually reading this. I printed out like all of BitTensor's documentation because I was trying to wrap my head around how everything worked. And I came to this part and I had to grab a pen and start highlighting things because I saw this line. BitTensor simply defines the market, which will reward. Like, okay, so we're going to have a market, we're going to reward. We're not going to define how you solve the problem. We're going to leave space for innovation around how that problem will be solved. And then we're going to open it up to thousands of incredibly talented individuals across the earth who achieve that aim in various and creative ways. Right? So it's starting to kind of click, right? I think people are maybe like, I don't know, I get goosebumps when I think about it. And the crazy thing about that is, I think I shared a link on Twitter recently, which was a video from Pete Shadbolt, who's the chief science officer of PsiQuantum. They're like one of the best funded quantum computing companies in the world. And I'm just going to play that video for you real quick, or just a section.
If I think about the history of the semiconductor industry, self-driving cars, rockets, robotics, and so many other technologies, to me, it really doesn't look like a story about breakthroughs. It's a story about grind and about sustained and dogged progress over decades. It's about leveraging capabilities from adjacent fields, about desperately trying to keep things simple. And most of all, it's about taking something that everybody said was impossible, something that's been impossible for decades, something that's failed and failed and failed, and dragging it, kicking and screaming, over the threshold of usefulness.
Right. And so I'm not the only person in quantum thinking about it this way. So I'm going to say, Pete, I'm going to go ahead and just, say that he's a bull too. And so, I mean, that we talked about, like, those algorithms getting better, but the only people that can innovate in quantum today are quantum people. Like, it's a very exclusive club. We opened it up with 63 and we invited BitTensor people to innovate, and they're already innovating in an incredibly impressive way, but we want to go a lot further. And so, like, I think most of you have seen the roadmap, and we'll get to it really soon, which is that we want all smart people having the ability to innovate in quantum, or even if you're dumb, we want anyone innovating in quantum, screw it. And so, like, when we started with BitTensor, and I told you I was a skeptic, like, so we came in here and I was like, yeah, okay, grift. We're going to find, that's just going to be grift. Like, watch your wallet. But actually we found, like, okay, there is a little bit, there's these little pockets of grift, but for the most part we saw grit, and we were sort of worried that, maybe it's going to be like a bunch of, mouth breathers. That is not the case at all. Like, we were blown away immediately by the intelligence that is created. It's not like and I don't even know if it's like it attracts intelligence or if it like fosters intelligence and grows it. And, we thought it would be people looking for easy money. And there is like a fair share of people looking for easy money, but like what we saw a lot more of was that the money goes to those who do hard work. And so, yeah, we've just been really excited with what we've seen here so far. Okay, so I told you I can be like a storyteller and just talk forever. So I better like breathe for a second. I'm going to take a drink of my coffee and pause, and then I'll totally keep going.
I don't want to interrupt you. I think everyone's loving it.
All right, sounds good. Well, we'll keep rolling then. Yeah, so far we launched the Quantum Subnet. And the Quantum Subnet on Subnet 63 focuses on giving users hard problems that have to be executed in a quantum environment. We're doing this because we want to get BitTensor educated on what a quantum circuit is, what quantum simulations are, how you can optimize a simulation, how you can understand the quantum mechanics that are working encoded into the circuit to optimize the circuits to find even more innovative ways to go. And I'm going to have Will, or Bongo Cat Feynman, take us through a couple of what those circuits are. So, Will.
Yeah, hi everyone. So my name is Will. For the past several years, my background has been in PhD research, academic research in atomic physics and quantum information science. And I'll say I'm a very new person to this whole qubit bit tensor thing. But in the short time that we've been here already, I've been super impressed by all the innovation and ingenuity that we've seen from our miners, and I'm really excited to see, where we go from here. So I think at this point it'd be good to dig into some technical details about what's already going on in Subnet 63, and we can take questions from anyone as they come. I think that'll be good. Okay, so we launched Subnet 63 with this idea of a peak circuit, right? And these peak circuits are a particular idea that have been launched recently by Scott Aronson and his collaborator Yushen Zhang. And they're an attempt to solve this open academic question of how do you verify what a quantum computer is doing, right? So you can say you build like a quantum computer. You say you build some like neutral atom experiment or trapped ion experiment or something, and you shoot them with lasers. You do whatever you want with the system, but how do you verify that the result is kind of doing what you want, right? This is an open research question, as I've said, and these peak circuits are kind of an ideal starting point for sort of a nice problem to have on the subnet for miners to solve for themselves to get them started understanding quantum. Because I'll get into the reasons why in a sec. So okay. Oh, that's weird. Okay, the slide control is weird. Okay, anyway, so what are peak circuits, right? So the fundamental thing to understand about quantum computers is that what they're doing is not actually so fundamentally different from just mere probabilistic computing. There's like some funny sort of complex numbers going on and wave interference and so on, but fundamentally what we're still dealing with probability distributions. And so the concept of a peak circuit is I'm going to leave it as a black box for now, right in the middle. And it's this kind of set of operations that you can do to take some initial sort of flat uniform probability distribution and introduce a peak on some particular computational state. So there's like a particular set of bit strings that are explorable in the system, and you pick one of these bit strings and you introduce some slight peaking in the probability distribution. And so the task that peak circuits sort of perform, right, is this peaking. And as a challenge to put out to the miners on Subnet 63, the task is to find the particular computational basis state on which there is peaking, and that's sort of the concept of a hidden bit string. So as I've said, this idea was originally put out by Scott Aronson and Yushen Zhang. There's the archive link for anyone who wants to take a look. I highly recommend this. There's some great insights, and it's actually a very approachable paper for people who aren't necessarily so familiar with quantum computing. But nevertheless, this problem is it seems to be a very reliable thing for the whole problem of verifiable quantum computing. And additionally, I'll say that it's a very approachable idea to people who are new to quantum computing in general. Right, the idea of finding this hidden bit string in the set of all others from this probability distribution is something that I think a lot of people can wrap their heads around, and it's as we'll see in a couple of slides here, well, it is the task for, well, it is kind of a usual thing that you might want to use a quantum computer for. It's not necessarily representative of kind of the rest of the quote unquote real problems that you might actually see in quantum computing. But nevertheless, peak circuits are also an amazing starting point because they're actually very hard to compute. Because physically, from a physical standpoint, the fundamental thing that differentiates quantum computing from classical computing is the existence of quantum entanglement. And specifically, this is exactly the thing that makes it hard to sort of simulate on a classical computer as well. When you have a lot of entanglement in the system, there's lots of extra information in the probability distribution that you will have to keep track of. It's typically thought of as sort of a distinct kind of entropy, in addition to sort of the classical Shannon entropy that some of you may have heard of. And this introduces a fundamental exponential bound on what's going on in the quantum computer that classical computers have to contend with. And the real thing about peak circuits is that, wait, let's see. There's supposed to be a graphic on this slide. Anyway, Bob, do you know what's going on?
Nah, man, your beautiful chart is not there. Hold on. You want me? I mean, I can try to see if I can get it to come back. You want me to try?
We can imagine it, right? It's the complexity of the circuit, and then the randomness or the entropy increasing in the complexity of the circuit, or the amount of entanglement.
Yeah, well, it was kind of supposed to be the layout of what these peak circuits look like, but I mean, it's not so important for what I'll say, I guess.
No worries. It was a sick graphic. I'm bummed, but that's cool. We'll screen grab it and throw it in the chat afterwards. I'll go see if somebody pulled it out of the Google Slides.
All right. Oh well. Okay. So anyway, so the idea behind peak circuits is that they are basically one step short of a completely random circuit. So you can think of just a random set of operations that you're doing to this quantum state, and there are lots of properties that people have proven about these random circuits, but one of them, just naively, is that they create lots of entanglement. And so this is where the real appeal of putting this out to the people on BitTensor comes from. So we know that they're used to throwing lots of compute at these problems. They're very good at managing all this raw power. And as far as we've seen on Subnet 63, they've done a great job of applying it to this problem of simulating peak circuits. But as I've kind of talked about a little bit before, one of the most fundamental things about being able to actually innovate in this space, in the quantum computing space, is that there are lots of trade-offs that you have to make. Right? The fundamental idea that basically all the research is pushing into is that you can very easily scale up your systems to sizes where this exponential cost kind of takes over and you hit basically a wall. Right? We're right at the frontier of kind of what's really doable on classical computers, and so what it really means to innovate in this space is to sort of, I'll co-opt what Pete was saying in the video that Bob showed earlier, right? Is that you have to really claw your way into sort of the space beyond the boundary, right? You have to drag your, in this case, the classical computers, kicking and screaming into the realm of the quantum as far as you can. And so one of the very prominent ideas in in the research that's relevant to this area is making trade-offs between accuracy and speed. So you can do a very poor simulation of a quantum computer, right? That could run very fast, but you won't be able to have high fidelity, of course, in whatever answers you get out of your simulation. Or you can spend a lot of time getting your accuracy right, but then your computation is going to take like 10 billion years. But I want to add sort of one third idea to this trade-off, and I'm going to say the whole idea of applying brute force compute to these problems is actually another contention, because what really needs to happen, I believe, and many other people that I work with believe, is that in order to really innovate, still, you need to also apply your brute force compute properly, right? That is, you need to all of this is open research questions. It's filled with hundreds of people and thousands of people in academia doing the same thing with coming from a different perspective. And so the real question is, can you also make algorithmic improvements? And this is something that I'm really excited for, because we're opening up these quantum problems to a wide range of people who are very good at managing raw power, and we're asking them to figure out what the best avenues are for applying that raw power. We're asking them, can you come up with new algorithms to be able to run these quantum problems and solve them in entirely new ways that no one has thought of? And so this is kind of a fundamental thing that I wanted to illustrate, a fundamental point that I wanted to illustrate in sort of the design of the second problem that we introduced to subnet 63, which we're calling hidden stabilizers. Now, hidden stabilizers are not sort of an established idea in the way that peak circuits are, but really we were designing this problem in order to really drive home this point of the fact that you can't just throw a bunch of computing at these problems. You need to engage with the underlying concepts. So we can go, I guess maybe this is a good point to take any questions from people if they have them on peak circuits. Otherwise, we can dive into the second problem.
So, can you explain a little bit more what you meant by the difference between accuracy, speed, and brute force? Like, what is this other dimension?
Sure. Right. So there exists, many different ways to simulate a quantum state in a quantum computer, right? And one of the leading, I find that this concept is most easily crystallized in that of the sort of matrix product state. Is that a familiar term?
The matrix product state?
Yeah.
Stefan?
You're summoning me into this. I have a different line of inquiry, but don't just entangle me into your own.
I actually am not sure about what the matrix product state is. I was hoping Stefan, my co-host, would save me.
Okay, yeah, totally no worries if it's not very familiar, right? I'm sure that people are familiar with tensor networks, though. Am I right?
I think a fair
No.
amount of the audience are quite AI familiar, but you might want to introduce it a little.
Sure. Okay. So tensor networks, right, are kind of a way of spreading out a sort of linear algebra-based computation among different parts, right? It's taking like a bunch of matrix math. In principle, it's like it's like multiplying a bunch of matrices together, but it's sort of decomposing it into many small pieces that are easier to manage, right? And one thing that I'm personally not an AI guy. I'm only a quantum guy, but from what I understand, a lot of these concepts are drawn from AI. So I'll speak from that viewpoint. So when you're working with tensor networks, right? There's this fundamental trade-off between accuracy and speed, where when you're sort of breaking your large computation into different parts, you can choose the precision with which you're doing the kind of decomposition, right? You can choose to throw away a lot of information in exchange for speed, or you can keep that information and have your matrices be a lot bigger, so that when you have to then go and do all the matrix multiplication, it just well, right?
Yeah, so it's accuracy, speed, and effectively cost.
Yes, that too. Cost is another factor. I guess usually people in academia don't think quite as much about the cost of these large.
Point.
Okay, but anyway,
I understand.
Yeah. Okay. So tensor networks. So matrix product states are kind of a translation of these tensor networks to the problem of simulating a quantum state. And it's a way to break your large quantum state vector. People traditionally think about it as sort of an array of like 2 to the number of qubits, number of complex numbers. But a matrix product state is sort of an answer to the question of how do I break this quantum state with some tunable fidelity into small little pieces in the same way that you would do for a large tensor network computation.
Understood. It's a matrix decomposition that allows you to parallelize the compute.
That's right.
I think
Yeah.
if I can dive in after that. So I certainly understand that within bit tensor we speak the language of what we call synthetics and organics. Synthetics are the things that keeps the machine warm and make sure the miners are doing something useful. Organics are kind of where the rubber hits the road, where real users inject their queries and the miners are hopefully, very well optimized to serve those queries with high quality responses. So these the peak quantum circuits are a really natural choice for, you guys have that sort of nice asymmetry where the validator can quickly verify, okay, the qubit strings match the probability distribution is strongly peaked around the expected area. Therefore, you guys can, reduce the amount of work the validator does. That also means that everyone in your subnet doesn't have to suffer from validators wasting their time and energy trying to recompute these really complex problems. But I guess the question from me is, do the peaked quantum circuits provide intrinsic utility? Like, are there organic queries that would map onto peaked quantum circuits? Does this actually, do you know what I mean? Does this track the production distribution of real use cases, or is this just a very useful heuristic to make sure that miners are doing things that aren't just sort of naive classical algorithms?
Mhm. Yeah, well, I'll say two things. First is that you were saying earlier that these have, in principle, nice value for validators, in that there's just like a single bit string that they check. I'll say that it is true, but in this case, one interesting thing that we've seen in terms of the operation of the subnet that we've been hearing about is that these peak circuits are actually quite hard to generate, and so I'll call out this specific feature of a lot of quantum problems that have been a major, obstacle in the theory for us to get over. Is that a lot of these quantum problems are very symmetric in terms of like how long it takes to create like a problem, like a circuit, right, and versus how long it takes to solve them. But then this is one of the things that we've done some innovation on ourselves in terms of optimizing all of these computations that have to be done to feed the beast, basically feed the beast that is all these voracious miners who are hungry to throw the compute at something. But then to your second, I'll talk about sort of the value of these peak circuits. Most of these peak circuits are not directly representative of kind of real quantum computing problems. And what our major aim was when we launched 63 was to start introducing these quantum concepts to maybe a crowd of miners who were maybe not so familiar. And so this illustrates some of the fundamental points. It's not directly a problem that people would solve, but it is a valuable research idea in terms of maybe like running some test benchmarks for a quantum computer when it's sort of initially constructed and making sure that it's doing the right thing before you then get on to the real worthwhile problems as we are planning to do in the next in the near future on 63.
Yeah, and maybe I'll jump in just a
Absolutely.
tiny bit.
Please. Yeah.
Yeah, no worries. And then hand it right back to you here, Crux, to pick up where you left off. But, the original value that Aronson and Yushan had in designing this was essentially to come up with an algorithm that you could use to actually prove that there was a working quantum computer. Like, how will you know when a quantum computer, like if you're giving them problems that are so hard that they can't be solved by regular computers, how will you know they got the right answer? And so you sort of need these problems that can be of lots of different sizes and complexities that somebody validating a quantum computer knows, but then it's so complex that only a real quantum computer can get the answer. And so verifiability was sort of the original use case. Now, how that maps into bit tensor is kind of really exciting because essentially, like in that model, the validators are literally the validators who can generate these circuits and understand what the final answer is supposed to be. But you can make these things like exponentially complex so that we can push the limits of what people can do. And so by incentivizing miners to go bigger and bigger, you're essentially encouraging them first to take existing simulation technologies and figure out how to scale those, like across large HPC, which is a really useful problem for the world who's trying to develop algorithms. But then second, it's to say, well, now they've designed these circuits to try to be like something only a quantum computer can do. Well, can you innovate in a way that allows you to scale larger than you would expect mathematically to be able to scale running on classical computers? And so when we do get into kind of like the roadmap and next steps, we'll sort of talk about why this first stage of like really pressure testing the community and seeing how they can scale it sort of translates into, I think, your earlier question, which was sort of around like you use some cool terms for like, one type of problem to kind of like get the community going. And then another type of problem that actually takes like almost like a two-sided market of problems and actually start solving them. And that's exactly the direction we're headed.
I believe I owe actually Mog Machine credits. He's the first person I recall using the term synthetic and organics. Back, a year and a half ago, everyone was just talking about synthetics. Like, how do you, procedurally generate problems on the fly that miners have to solve? And then obviously there was a point where subnets had to actually serve real user queries, and that's where organics came in. So I'll take no credit for the language there. I'll give Mog Machine the credit. But you guys are giving me a million jumping off points here. I'm aware that you've got probably loads more great slides to get through, so maybe I'll just hold off and let you guys crack on.
Sounds good. Well, don't let us stop you, but we do have some exciting ground. I have a feeling that by the time we sort of start dropping some of the big things that are coming next, these questions will sort of like, interest may have moved to the big things coming next. So please don't hesitate if you have things that you want to make sure we hit to hit them before we move on. All right. So Will, maybe I'll hand it back and you can keep rolling into HSTAB.
Sure. Yeah. Sounds good.
And maybe one of the things that, maybe we should contextually say is sort of why we introduced HSTAB so quickly.
Right. Exactly. Yeah. So I guess I'll return to this trifecta of accuracy versus speed versus brute force compute, because as I was mentioning earlier, right, a huge part of what innovation looks like is coming up with new algorithms and really interacting and engaging with sort of the quantum information that's going on behind the scenes. And so this was our attempt to really illustrate the point of this third dimension to this trade-off here. Because what we're going to be talking about is sort of what's known as the stabilizer formalism. And so this the stabilizer formalism it really underpins a lot of the current research of quantum error correction. This is a very hot area of research because it's basically the thing that will allow quantum computers to scale much larger than they are currently. One of the things about quantum computers is that they're very prone to sources of error and noise, but error correction comes in and solves this problem in the same way that classical error correction does, but it's much more complicated because there's different sort of quadratures of degrees of freedom that are involved with the physical qubits and so on, and we don't have to get too far into that. But what I want to talk about in terms of the stabilizer formalism as it applies to 63 is that it's all very mathematical, right? There's a lot of nice theory and math that goes on behind the scenes, and what we really want to do going forward and leading into the rest of our roadmap is to introduce these concepts and make sure that our miners are at least familiar and preferably quite comfortable with all these concepts so they can make major improvements as we go on. So when I talk about stabilizers, when people talk about stabilizers, they often talk in terms of these special sort of single qubit matrices, these X, Y, and Z. Right, so these are 2x2 complex matrices, and a lot of what goes on here is building lots of mathematical structure on top of these small little moving parts. So what we're talking about here are these three matrices in addition to the 2x2 identity, and we talk about sort of the set of all these are called Pauli matrices. They show up all over physics and even a lot of kind of pure math, right? So these are Pauli matrices, and we can talk about the set of all sort of n-ary tensor products of them. So I have this curly p sub n. We can talk about the length of, we call them Pauli strings. So these are tensor products of Pauli matrices up to an overall sign that's plus or minus. And we're going to talk about n-ary Pauli strings that correspond to operators on the space of n qubits. So you can imagine a register of n qubits in a quantum computer, and then these are special operators that we can apply to them. They have a particular property that for a certain kind of subset of all possible quantum states, the state can actually be entirely specified by a set of, some number of these n-length Pauli strings. And we call those stabilizers. So each stabilizer is a Pauli string of length n, and we can use some number of these Pauli strings as the stabilizer set, which I'll call the stabilizer set that completely specifies this quantum state. And so this is one of my favorite pieces of quantum information, actually, because it's an entirely different approach to specifying how you can represent a quantum state in a computer's memory. As I've said before, people are usually used to thinking of state vectors as these 2 to the n length complex valued arrays of numbers. But instead, you can treat them as just bits in an array, as I'll show on the next slide. Whoops. Okay. But one really key property that that the subset of stabilizer states have is that you can actually get a computational advantage through reasoning about these small little parts and this alternate way of specifying a quantum state. And it takes the form of sort of a Clifford algebra. This is the mathematical formalization of how you can multiply all of these small little pieces together. And what I'm showing over on the left here is sort of the key multiplication table that characterizes what this Clifford algebra sort of behaves like.